So this is my title, Coordinates Along Neck Pinches for Moduli of Convex Real Projective Structures. And this is joint with Tengren Zhang from National University of Singapore. Okay? So the main thing that I'd like to discuss today is an analog of a fact in kind of the in the geometry of the Deligne-Mumford compactification mg bar that is in kind of this more general case of convex real projective structures. And so so the first thing that I'd like to talk about is some things that are. So I'll talk about a little bit. I mean, some people have, of course, introduced some of these concepts. So I'm going to talk a little bit about Finchel-Nielsen coordinates and mg bar, which is the Deligne-Mumford compactification. So this is mainly going to be from the point of view of hyperbolic geometry, not the point of view of algebraic geometry, but I'll mention maybe a tiny bit about the algebraic geometry. So, so let S be a closed oriented surface of genus G at least 2, and I'm going to let sigma be kind of put a natural hyperbolic metric on S. So just kind of a Riemannian metric with curvature -1. And so then, of course, by the uniformization theorem, this is equivalent to putting a complex structure on S. And so what I'd like to do is to consider this surface. And so as is well known, we can find a maximal collection of, so this is going to be what's known as a Pants decomposition. And so this is going to be formed by, you take several simple closed curves, which are in different homotopy classes, but that do not ever intersect. And in the non-compact case, which we'll come to in a bit, then they will also not be peripheral. Then in this case, for each of these free homotopy classes of loops here, then there is a unique, so these can be represented by hyperbolic geodesics. So you can kind of cut by hyperbolic geodesics. Okay? And so then there's kind of a well-known theory that's originally due to Fricke and Klein that you can so you can recover kind of coordinates on the space of marked hyperbolic structures on S. So I guess I'll call this Teichmüller space. Some people in this context like to say Fricke-Klein space. And so the way you do this is to, so for each of these curves, in the Pants decomposition, we're going to have two numbers. We're going to have a length that will be, say, Li, and that's just going to be the hyperbolic length. But then, in addition, there's going to be another number, because even if you have, say, well, we can just consider this curve here. If this has length Li, there are two kind of inequivalent ways. There's more than one inequivalent ways of putting these things together to make a hyperbolic surface, which correspond to kind of twisting one side before you glue it to the other side. And so, I mean, the neighborhood of this hyperbolic geodesic looks very nice. So this kind of twist does not still kind of preserves the hyperbolic structure. And so I'll say kind of a twist, theta I, and this is going to be real valued. Okay? And it'll be useful for us to, so I will kind of also talk about a special sort of twist, Dane twist. And so for this is going to be, we can kind of correspond. You have to have some normalization to define these kind of twist parameters, but this will correspond to the twist parameter going up exactly by 1. And the normalization that I will choose is that this means this is going to be 1 kind of full rotation. Okay? And so you can imagine kind of 2 hyperbolic structures. You put them together this way, but then after a Dane twist, it's like you rotate by a full 360 degrees before you turn them like this, before you put them back together. And so in particular, Dane twists, these are going to be elements of the mapping class group, which I might kind of write as a mapping class group of S. And in that, they, that kind of the 2 hyperbolic structures are isometric, but do not respect the underlying marking. So one way of thinking about the marking is you could kind of choose a basis for H1 homology or something like this, or you could have kind of a fixed homeomorphism to a given surface of the same genus. Good? All right. So, so for this, I'll define kind of the moduli space. Mg is going to be the Teichmüller space mod out by the natural action of the mapping class group. And so this is quite a nice action. So it's properly discontinuous, but it does have some fixed points. So in general, this space will be kind of an orbifold of the same dimension. Of, again, dimension 6g minus 6. Okay? So one of the things that we're going to discuss is kind of, just to some extent, kind of the nature of this orbifold, but from kind of a slightly non-standard point of view if you're used to kind of the algebraic geometry picture. So, I mean, in particular with Mg, and later on when we talk about Mg bar, you know exactly which points are singular under this orbifold action. These are exactly going to be the hyperbolic structures that have extra automorphisms. So if genus is strictly above 2, then that's kind of any non-trivial isometry that's not isotopic to the identity map will give you kind of an orbifold point. Instead, when we go to Mg bar, we're going to take kind of a slightly different point of view and find some kind of smooth coordinates that are more really analogous to this, which in this case, this is the universal cover of Mg. Good. All right. So there's a natural compactification due to Deligne and Mumford. So this is going to be a compact space. So this also, I mean, so this also is an orbifold. It's, I guess I haven't talked about this. I mean, Teichmüller space has a complex structure, and this is going to be a quasi-projective variety, or I guess more generally, Deligne-Mumford stack. But this will be compact with a nice projective complex structure. And so kind of the question is what to add at the boundary? Good. So what sort of extra structures do we need to do this? And so then I mean, from the point of view of hyperbolic geometry, I'm going to, I guess, talk about 2 theorems So one is theorem of Mumford is that so for all epsilon bigger than 0, this moduli space Mg minus those sigma with hyperbolic systole less than epsilon is compact. So this is Mumford's compactness theorem. And there's another result, which I guess, which is known, at least in generality of, in more generality as a Margulis lemma, is that if epsilon is small enough, so there exists a small epsilon naught, such that for all epsilon, positive epsilon less than x naught, the thin part of, so this is going to be sigma minus the points, let's see, p n sigma such that the injectivity radius at p of sigma is less than epsilon. So in other words, if there's no kind of ball of radius, so in terms of the hyperbolic metric, we kind of throw away the points where kind of the ball of radius epsilon doesn't inject under the exponential map, is kind of well described. Okay. No, I guess the thin, what I wrote down was the thick part. So the thin part is just the part with the small injectivity radius. And so in particular, there are, this also extends to kind of, to complete hyperbolic structures, not just compact ones. And so in particular, what we have here, there are two phenomena. And so this is going to be an L. This is going to be smaller than, say, 2 epsilon. So one, we have what's known as a collar neighborhood. And but then it's also kind of possible to take the case L equals 0. And so in this case, we're going to have, shouldn't go together, but we're going to have, this would be kind of 2 cusps, for example. And so this may have kind of a picture like this, okay? And so in particular, the content of this Margulis lemma is that, well, for these epsilon small enough, these are all, the only parameter here is the length of the geodesic, right? So we have, everything is going to be parametrized by L, which is, say, smaller than 2 epsilon, and L equals 0 is allowed in this degenerating limit, okay? All right. So in particular, together, these two, in order to kind of find a compactification, then one should kind of just determine how to kind of handle just this sort of degeneration, where kind of the length goes to 0. And so what we can do is we can kind of add in these kind of L equals 0 cases. So this, we may call this, say, a neck pinch, because this, this kind of neck or collar, the radius, I mean, the L is the circumference here is going to 0. And so this can be done, so this is possible along any multicurve. And so this is a multicurve not in the sense that Gabriele was talking about earlier, is these are going to be, so multicurve in the sense of kind of simple closed curves, free homotopy classes of simple closed curves that don't intersect each other and are, so they're each simple and they don't intersect and there's no multiplicity. Okay? So this is kind of the content of this. But in particular, what I'd like to do is to show that there are some nice coordinates here. And so, in particular, in terms of the Fenchel-Nielsen coordinates, we may have kind of the following. So this is kind of quite a large length here, but if in terms of, so let's assume we have some fit, we take this, this single, I guess we'll just not, I'll not worry about this, but let's say we have a pinch decomposition, but I'll just only look at the case where this neck is being pinched. And so in particular, so what happens here is that so as kind of this length gets smaller, the transverse directions get larger. Maybe I won't put this in the picture. And then so we go down to the case where we have kind of these two kind of finite area hyperbolic structures on this. So in particular, in terms of the Fenchel-Nielsen coordinates, we let L goes to 0. But then we also notice that the following, which is that so at L equals 0, theta, the twist parameter is irrelevant. Because, I mean, the twist parameter is what you get. This is the parameter of if you have two of these, if you cut along this geodesic, then you twist and glue them back. But these are no longer attached, right? So we want to ignore the twist parameter in this case. And moreover, kind of this is, so the L and theta are at the level of marked structures. And we really want to kind of have a nice consideration of the unmarked case in the moduli space after you mod out by the mapping class group. And so in this case, what you also want to do is you want to mod out by the Dane twists along whichever multicurve you're collapsing. So I'll just call this one, this multicurve C. Okay? So this is just going to be the group, the subgroup of the mapping class group that is in terms of modding out by Dane twists. Okay? So the idea for this is that what we can do is we can find kind of coordinates on, so the Teichmüller space, I guess I'll call this S instead of G. And I'm going to say that this is going to be AUG, which is going to be augmented at C. So what that means to be augmented at C is I'm going to exactly put in structures that look like this, which have kind of, in which kind of C has degenerated. So, and then I'm going to mod out by the Dane twists just along C. So in this case, that's a single curve, could be a multicurve. Okay? And so for this is going to be equal to the following. What we can do is so I guess I'll call, just kind of to number these things, this C, this will correspond to, L1 and theta 1, the length and twist coordinates. So what we can do instead is we can replace this by, let's see, L1 e to the 2 pi I theta 1. So this is going to be a complex, not a holomorphic coordinate. And then the other ones, for the other coordinates corresponding to curves that we do not pinch, such as these over here, then we just have the kind of the standard Fenchel-Nielsen coordinates. Okay? And so this exactly takes care of the case, well, when L1 is equal to 0, theta doesn't matter. And we mod out by Dane twist, which we've normalized to be kind of just adding 1, and so you do have something like this structure. So this gives us natural coordinates. And this is, I mean, it's what you might expect from kind of orbifold coordinates, because, I mean, you kind of project down. So these are naturally kind of smooth coordinates. And but it's not quite exactly what you would get from an orbifold coordinate, because there's no kind of finite group action here. Instead, you just have kind of this coset space of the mapping class group mod out by these Dane twists, which is not finite and not a group. But this is kind of, but in terms of the hyperbolic geometry, this is kind of a standard way to handle these sorts of things, these sorts of coordinates. And so this is the picture that I'd like to generalize here, okay? And I'd like to do one more thing in terms of this picture. It's also natural to kind of to look at this picture in terms of what's known as a geometric limit. And so this is it's kind of the point of view. I think back in I think 1970 or so, in the 1970s. Of Bill Harvey is to look at this from the point of view of geometric limits. And so what you're going to do is we're going to have this, this family of surfaces which are going to degenerate along this simple closed curve. And what I'd like to do is, I mean, in this case, this is going to be a separating curve, but I mean, the non-separating curves, you can make sense of this as well. I'll pick out 2 points here, P and Q. And then I'm going to see what happens as L gets smaller. So, so I guess maybe I'll kind of make L relatively small here. And then we have kind of a case with P and Q where, so this will be the case L equals 0. Okay? So what happens here is that from the point of view of P, I want to kind of lift up to the universal cover, which is the hyperbolic plane, and kind of find a point P, and I want to lift this curve to a geodesic. And it's going to be useful, so I'm going to lift kind of C to a geodesic, C tilde, and it's for projective structures, I'm going to use the Klein model. So I'm going to draw my geodesics as hyperbolic geodesics as straight lines. And similarly, you can kind of lift, so I'm going to draw a different picture. I'm going to lift Q here, and I'll draw kind of a different kind of geodesic here. So this will also kind of be a copy of C tilde. So they're not, these pictures are not exactly the same. But then what happens in the limit is from the point of view of P, the metric has become complete here. And so if you draw kind of this Klein model in P tilde, then this geodesic has just kind of corresponds to a point at the boundary, right? And similarly over here for Q tilde, this geodesic corresponds to a point at the boundary. Okay? So this is kind of known as a geometric limit. This is kind of well known in hyperbolic geometry, Riemannian geometry. Kind of fix a base point, and then kind of you look at kind of the things that are finite distance from that base point in terms of, say, the exponential map. But I'd like to see what happens here is we can also describe kind of this gamma. This is going to be a Fuchsian group. And so I'll describe this as, so this is going to be, in our case, this is going to be in the isometries of the hyperbolic plane. And so for us, this will be, since we're doing the Klein model, P021. And so in this case, and we'll consider kind of the case gamma I going to gamma in some sense. And so what happens here is, in terms of this, is that we have, so we may have gamma I here. And these pictures are not exactly the same, but what you do is you conjugate by a, so sigma I is going to be some element in, say, PO21. Okay? And then in the limit, this will be, so what happens is, in this limit, we may have kind of gamma I going to a Fuchsian group gamma, but then sigma I, gamma I inverse, this conjugation going to, say, gamma tilde, like infinity. Okay? And so this conjugation diverges here, and that's kind of the content of this geometric limit is that, I mean, if you normalize such that this group is gamma I, then this one you have to conjugate. And these pictures are different because of this, the conjugation gives you different limits. Okay? And I guess I should restrict to, I'll call this part S1 and this S2. This is restricted to pi 1 of S1, and this is restricted to, no inverse there, pi 1 of S2. Okay. So this is kind of from the point of view of geometric limits at Harvey, this is kind of the structure that we've constructed. And I guess in terms of just group theory, this is known as an example of the Schaposnik topology. And that's what I'd like to, so this is kind of the picture that I'd like to generalize. Okay. So the next thing is, and I'd like to thank Dick for mentioning some of this earlier, is to talk about convex real projective structures, or more simply RP2, since this will be an XG structure with homogeneous space RP2. So by the way, are there any questions about this so far? I mean, probably to some people this is quite familiar, but I'm not sure everyone. Yeah. Yes, yes, and then the Schaposnik topology has kind of a mechanism for ignoring all the stuff that diverges. So I think I'm going to have to pay a little bit more closer, at least I don't know, I didn't write down the details for what happens in this convex RP2 structure case, and I'd have to pay a little bit more attention to this sort of restriction. Yeah. Any other questions? Or? Okay. All right. So this is, so I'm going to take a convex bounded domain. So this is going to be bounded in some R2, but you think about this in terms of inhomogeneous coordinates inside of RP2. And I'll consider a, so this is going to be, I guess I might call this the image of the developing map in terms of the geometric structure. And also I'll have kind of a gamma is a representation of the fundamental group that's going to be faithful and properly discontinuous. And that will go into the projective automorphisms of gamma. So this considered as PGL3R inside of PGL3R. And kind of the basic condition that I want is that this is going to be diffeomorphic to S, or homeomorphic to S, and in particular, this is this induces a convex RP2 structure on S. Okay. So the convexity is that omega, which is the image of the developing map, is a convex domain, bounded convex domain. And the RP2 structure is just that there are local coordinates that, when you, in RP2, that are glued together by maps in PGL3R. Okay? All right. So it's going to be useful for us to, so I'll define kind of a marked convex RP2 structure by the following. So the set of such omega and gamma with these conditions here, mod out by an equivalence relation. So the equivalence relation is given by, for sigma, an element of PGL3R. Then sigma is going to take omega and gamma to, you just translate omega by sigma, and you conjugate gamma. Okay? And so this is exactly the same sort of thing that we saw over here. It's just that with a convex RP2 structure, at least in the generality that I will need it, I need to kind of carry along this domain as well as the representation gamma. Okay? Okay. And so, in this case, of course, with the Klein model, there's, the Klein model of hyperbolic space, then there's no need to kind of keep track of the domain because it's always just a disk. So, but in this other case, this may vary. Okay. So there's a theorem due to Goldman, which Dick also mentioned before, is that given a Pants decomposition on S, then we get, so I might kind of call this this deformation space. I'll write it G for Goldman sometimes. This is going to be homeomorphic naturally to R16G minus 16. And what will happen is we'll have some various coordinates corresponding to the Pants decomposition. So okay, so this is a standard picture, and so for each curve in this Pants decomposition, we get two length type coordinates. These will be these will essentially be kind of the eigenvalues of the holonomy in SL3R. Okay. So these correspond to the hyperbolic length, or generalize this. We're going to get two twist type and two on each. So this is going to be on each curve, and then on each pants, each pair of pants, we get two interior parameters, which are a bit less geometric. So I'll definitely talk about kind of the length and the twist parameters later. But I mean, in terms of if you kind of add all these up, you're going to get dimension 16G minus 16. Okay. So so you notice that this is more complicated than the standard Fenchel-Nielsen picture in that there are these interior parameters that are not associated to curves but to the pairs of pants. Okay. All right. So, all right. So, what I would like to do, so let C be a multicurve in this sense on S, and then I'm going to define a marked, what I'll call a regular convex RP2 structure on S minus C is a convex RP2 structure on S minus C, which is a non-trivial geometric limit of convex RP2 structures on S, which degenerates degenerating along this multicurve C. Okay? So in particular, what I will so what I can do is, I mean, if I cut along these three multicurves, then you notice that S, there are going to be two connected components. And so in general, there may be multiple connected components. So S is a disjoint union of these connected components. And then for all of these Sj components, there exists sigma I, and there's a sequence in PGL3R. So this also depends on J, but I just don't want to write too much stuff. Maybe I'll put the J up here, such that sigma ij acting on omega I, gamma I, converges to some oj gj, and the oi mod gi, this is a convex RP2 structure on this component Sj. OJ, GJ, okay? So basically what you do is, I mean, you cut along this, and then you get kind of this convex real projective structures on these limiting pieces. And this would be similar to kind of just these hyperbolic structures here in the limit, which are pictured there. And I guess one thing to note is that, yeah, so you do need these sorts of, these various sequences, one for each component, and they will, I mean, mutually diverge, these for each of the components, just as in the hyperbolic case. All right. Okay. So, kind of some so let me kind of mention the theorem, and then kind of talk about some motivation, and then kind of go on to some of the ideas here. Is so this is for all C, a multicurve in S. We can produce coordinates on this kind of Goldman space augmented just along C in terms of this, these sorts of limits. Again, mod out by the Dane twists along C. So this is going to be R16G minus 16 by kind of combining and extending Goldman's coordinates. So these length type, twist type, and interior type coordinates. Okay. And so I guess maybe it may be a good time now to talk about a little bit of motivation. So why would are we interested in this? So there's an earlier theorem that I proved. So I think it's on the archive in 2015, but it's to appear at some point in JDG, is that this deformation space of, if you augment along all multicurves, and you mod out by the mapping class group. And so if this were just, if this is kind of the Teichmüller space augmented modding out by the mapping class group, this is essentially Harvey's construction of MG bar. So we're doing this instead of the convex RP2 structures. This is homeomorphic to the total space of a vector bundle over MG bar, and this vector bundle is going to be the third tensor power of the relative dualizing sheaf. So over a smooth curve, this is just going to be the dualizing sheaf is just going to be the canonical bundle. And so the third tensor power, that would be what's known as cubic differentials, just things that are like dz cubed, right? And so it turns out that there's a natural way to extend this over mg bar in terms of where instead of looking at it in terms of the hyperbolic geometry, each of these singularities would be a complex node. And that would be known as something called regular cubic differentials, which I don't have time to really discuss so much. But but kind of the basic fact is that this space is a vector bundle in the right category over mg bar. And so in particular, this entire thing has the structure of an orbifold. Yep, question?
So, like these augmented coordinates, do they only exist when you quotient by density, or it seems like
no.
you can lift that then also as the
Yeah, so if you do this stuff, if you augment, I think if you just augment along a single multi-curve, then you're kind of putting some stuff at the boundary of Teichmüller space, which you can think of as like a big ball, at least homeomorphic to it. But when you do this, it's the space that you get is not locally compact. And in particular, kind of Dane twist actions give you kind of a group action, which shows you kind of the non-compact direction. Because I mean, when you add in kind of this nodal curve, then the Dane twists don't do anything to that. But in a neighborhood, there's this Z family of Dane twists.
So you sort of pull back like this
Yeah,
aggregation of the quotient
yeah, yeah. And so you define this as a topological space, which is not very nice. But once you kind of you have kind of a nice space here. This is a mapping class group, so this becomes an orbifold. But this is actually a little bit better. This is I mean, at least what you would think of as kind of manifold coordinate charts. I mean, even though kind of this quotient action is not a finite group, that this is, at least from the point of view of hyperbolic geometry, this is the nicest place to put manifold coordinate charts. Okay? All right. Any other questions? Or this is global. Yeah. This one is global. Yeah. I mean, this one I pick a multi-curve, but when I say augment it here, you augment along all multi-curves. So, but then when you quotient out by the mapping class group, if this were just hyperbolic structures, you just get mg bar. This is Harvey's construction. Okay. All right. Well, what? That's true. That's true. So what did Harvey do? Yeah. So Howie Mazur. I don't know. Yeah. Yeah. Okay. That's. Okay. Yeah. I think I'm not gonna. I'll defer to your judgment. I mean, at least from my point of view, there's kind of some. Yeah. The literature is rather confusing, given that there were a lot of things that were referred to that never appeared. And so, yeah, and yeah. So, yes, I will. Yes. So, sorry if I misattributed things. Yeah, but in particular, this this is kind of the point of view that's going to be useful for this talk. Okay. All right. So so in particular, you expect to kind of have this sort of manifold coordinate charts. So this is one motivation. A second motivation is, so I call this theorem 1, is so for this, you get kind of a geometric idea of the limits. Because, I mean, this topology is rather abstract. I mean, the Chabot topology over here is rather abstract, but then we know that there's only kind of one sort of singularity that can happen. And so then part of the story here is, well, I'm going to give you kind of an expanded menagerie of singularities and show you what can happen here. but in terms of the Finchel-Nielsen coordinates, then you can see an awful lot about what's going on in terms of the limits. So I guess one thing that we can do with this, we can simplify the proof of Theorem 1, because I didn't address this quotient in Theorem 1, and in order to do this, I heavily used the compactness of mg bar, which I don't have to do from this point of view. And so maybe I'll just say maybe more general Hitchin representations, as Dick was talking about. So these would be kind of these sorts of limits of Hitchin representations for PGL3R, but then of course PGL-DR for higher D is also very interesting. And kind of from this point of view, a lot of this has analogs, which, I mean, I haven't thought about the details at all, but okay. All right. So okay, so so these are the regular convex RP2 structures, and I'm using the word regular to mean singular but not very bad. So this is like if you take an ODE course as an undergraduate, you learn about regular singular points. And I mean, some of the analysis from the point of view of the cubic differentials does correspond to this via some relationships to Simpson's theory and parabolic bundles and things like this. But so I'm using the word regular to mean kind of tame sort of singularity. And there's kind of a basic fact, which goes back a long time, is that so for kind of S compact, so for with a convex RP2 structure, so S compact, and the genus is at least 2, of course, I'll call this X on S. Then for all non-trivial loops, the holonomy is what's known as, and this is kind of a bad terminology because I've already had to use the word hyperbolic in another setting, but I think this is fairly standard. It's hyperbolic. And what that means is that it's conjugate to, if you, so in terms of the holonomy of the loop, you can kind of, this is an element of this representation into PGL3R. You can lift this easily to SL3R. And so this is going to be the case. So all these are going to be distinct positive eigenvalues. And then to be an SL3R, we'll, so this is an SL3R. Okay. So all non-trivial loops are hyperbolic. And I mean, and I guess Dick drew this picture earlier about how you can kind of look at their three fixed points in RP2, which correspond to the eigenlines in R3, and say a lot about kind of the geometry here. And so in particular, you may have, let's see, so this may be omega. And so I'll call this the 3 fixed points plus, minus, and 0. So this is going to be the attracting fixed point. So this is going to be essentially the image of the eigenline of, so this is going to be in RP2. So this is going to be the fixed point corresponding to lambda 1. This is going to be for the smallest eigenvalue, lambda 3. And then the other one is the fixed point for lambda 2. Okay? Okay. And we have kind of the following dynamic picture in this, which is known as, so this is going to be the principal triangle, and this dotted line is the principal geodesic. Okay. And so in the compact case, then this is all that you get. But in terms of these degenerations, then we're going to pick one of these simple closed curves, or in general a multi-curve, and allow degenerations along that. And so then this, the structure can degenerate here. So we have kind of, there are 4 types of generations. So in terms of hyperbolic geometry, there's a single type of generation. There are more now. So this one is going to be what you might call parabolic. And this actually corresponds to kind of the picture of this parabolic element in the Fuchsian group under the Klein model. So this is going to be this full Jordan block with eigenvalues 1. And in terms of this convex RP2 structure, you have there's a single fixed point here. But then there's also a line, which is going to be tangent to the boundary here, on which this on which the holonomy acts. Right? And so this is the analog of kind of what happens in MG bar. But then there are 3 others. Well, depending on how you want to count things. So I'll say the quasi hyperbolic. So this again is, so you notice that in the compact case, and again, if as long as your curve is non-peripheral, you're required to have these, the eigenvalues be separated. So if all 3 come together, you get this parabolic singularity, but 2 of them can come together as well. And so you could say have something like this. So 2 eigenvalues come together here. And the limits that actually occur are always going to have full Jordan block. So these are going to be, so I guess I'll do the case where lambda 1 is bigger than lambda 3, but that doesn't really matter. And so in this case, we have the following. So this is going to be, this would be, let's see. So this is the fixed, so lambda 3 is definitely repelling, and the other is a little more complicated, fixed point of lambda 1. And so what happens in this case is the domain omega is going to be tangent to this line, and it will also be tangent to this kind of line on which kind of the lambda 1 block acts parabolically. Instead of this picture. Okay, and then similarly, we could switch the order of these 2 things and reverse the arrows, still call that quasi-hyperbolic. And then there are other cases where there are 2 other cases, so maybe I'll kind of call these over here. This is going to be, maybe I'll draw the pictures first. I'll call this bulge plus infinity and bulge minus infinity. And so in this case, the holonomy will remain hyperbolic. But with bulge plus infinity, what happens is the image of the developing map will fill out the entire principal triangle. And with bulge minus infinity, the image of the developing map will stop at the principal geodesic and not have any of the principal triangle. Okay? It turns out these are paired because you know that, so, and if you think about the algebraic geometry, a nodal curve always has 2 sheets here, so I have to, this is just 1 sheet, and so I need to show you the other side. And so, so these are paired in kind of opposite ways. So a bulge plus infinity would be paired to a minus infinity and vice versa. Okay, and so in this case, the holonomy remains hyperbolic. It's just that kind of the developing map is different here. And that's actually the reason that I have to kind of keep track of this omega as well as the gamma i's in my definition of convergence, because you can construct on kind of a non-compact surface convex projective structures of identical holonomy, identical gamma I, but they have different developing maps in terms of this bulge plus and minus infinity. And we have to keep track of that. So you can't just consider the limits of the holonomy. You need to consider this as well. Okay. So let me say kind of briefly what bulge is. And these are things that we have to kind of normalize in a different way in our paper, but I'll just say this in kind of an easy way to think about it. So if we have kind of the holonomy, hyperbolic holonomy is the following. So again, these are, so then we have kind of the length parameters. So we'll call this log of lambda 1 over lambda 2 and log of lambda 2 over lambda 3. Oh, by the way, for the hyperbolic case, if this came from a hyperbolic metric, then lambda 2 is going to be equal to 1. And so this does correspond, at least up to some scaling, to the hyperbolic length. And then in order to attach across a loop, in order to twist, we don't just have kind of one way of twisting, but we can twist by any matrix that will commute with this. And so in SL3R, these are again going to have to be diagonal matrices. So I'll call one of them twist. And this kind of corresponds to the usual hyperbolic twist. And the other one, bulge. Which will be like this. And so this will kind of give you, so Goldman's generalized twist parameters will be kind of a twist and a bulge. And I guess one thing to note is that when you're attaching these things across the geodesic, then if this bulge parameter goes to plus infinity, that corresponds to the middle coordinate here becoming very large, and that will be kind of filling out this triangle towards this fixed point. Okay. The distance across, yeah. Yes, the distance does, yeah, that is true. Yes, the distance in fact should change. Yeah, I think that does happen. And I guess when I was talking about when I was analyzing the cubic differential case, I had to do this. There's a natural invariant Riemannian metric called the Blaschke metric, and I had to analyze that, what happened along those necks. But this is kind of it's known to be uniformly equivalent by results of Benoit and Hulin to the Hilbert metric, for example. And there's a tight relationship. I think Tolzol did this. Yeah, you can do things like that. And then, of course, I mean, in the limit, that doesn't really carry much geometry, so you want to make sure that you're in. So that was actually one of the points in my first paper, is that you want to make sure you're in the thin part. But it's not actually thin in terms of injectivity radii, so you have to do something else, and it ends up being kind of messy. So. Yeah. Any more questions? Okay. Okay, and I guess one of the things I proved in my first paper is that these are all the degenerations that can happen. This is all that can happen. Okay, so now what I like to do is I want to write down these Finchel-Nielsen type coordinates, which are going to be modifications of what Goldman did. So this is going to be on this Goldman space augmented along C, mod out by Dane twists along C. Okay? So here, what I want to be able to do is, so the L1 and the L2, this is going to be L1 and L2, this log of the ratio of these eigenvalues. And you remember the degeneration is when one or more of them come together. So that would correspond to allowing the value 0 here. So from 0 to infinity, these are kind of, Goldman showed that you can get any of these parameters in terms of his space, but actually allowing 0, this is the augmentation in this case. Okay? The next thing that I'd like to do is, so I'll call kind of the bulge, and I'm going to use different letters. So maybe I'll kind of call this one B and this one theta, like I did before, just because these are not actually what we use. We have to normalize and things a different way. So theta, the twist, so this is going to be the twist. This is going to be in just any real number. But you can kind of think about this is what you want to do is you want to mod out by Dane twists. Okay? Which when you normalize will be kind of theta going to theta plus 1. Okay? And then the bulge, well this, we're going to augment this by allowing the values plus and minus infinity as well. But when this happens, we have various degenerations. So, so with kind of the following degenerations, if the bulge is plus and minus infinity, then we actually are not attaching the two sides here. So I mean, there's nothing to attach here, and so the twist parameter is irrelevant. So we throw that away in this case. Also, if the kind of the holonomy degenerates in that one or both of them, these L1, Li go to 0, then in that case, the twist and the bulge are both irrelevant. And then we're going to mod out theta by z. Okay? And so this was, so this is not that simple a formula, but it corresponds to just the L times e to the 2 pi I theta that was hopefully easier to see in the hyperbolic case. And so one of the first things that we did is that when you do this, when you take, so I'll call these identifications just an equivalence relation tilde. So one of the first things that we did is I'll call this space E, which is so this is homeomorphic to R4. So just like kind of this L e to the 2 pi I theta is homeomorphic to R2. So you kind of and this is something that that you certainly expect, given kind of that I showed earlier that this was an orbifold. But this kind of encodes a lot of the geometry of these structures in kind of in quite an explicit way. And so then the theorem. So again, C is going to be a multicurve with let's say, with n components. G is going to be the genus of S. And then what we're going to do is we're going to complete C to a Pants decomposition of S. So you may need to draw in some more curves until you get everything down to pairs of Pants. And then the theorem is that this quotient of the augmented space along C mod out by the Dane twists along C is homeomorphic to e to the n cross r to the. So these are going to be the interior parameters for the pairs of Pants cross r to the 2 times 3g minus 3 minus n. These are going to be the twist and bulge parameters of the remaining elements of the pairs of Pants. And then we're going to have r plus times 2 to the 3g minus 3 plus minus n. These are going to be the length parameters. OK, and then this all is homeomorphic to r16g minus 16, if you count this up correctly. OK. So I guess one thing to note is that, so one of the things we had to do was, well, I've kind of ignored the interior parameters. And the reason, but it's not clear, say, from Goldman's work, and I guess I think Ludovic Marquis also had some subsequent work on the non-compact cases. But even in those cases, from what was in the literature, it wasn't clear that the interior parameters really had to behave well under these families of degenerations that we considered. And so we have to really kind of work to kind of write these down in a nice enough way that we'll be able to handle these in families. And for this, we kind of use work of Fogh-Goncharov and then Banahan-Dreyer and then Zhang earlier so they had kind of some better ways of viewing these interior parameters, which we exploit. And we also have to kind of find a nice way of kind of normalizing the twist and bulge. So I mean, in terms of kind of the ordinary Finchel-Nielsen theory, you can kind of draw some kind of geodesics between kind of if you have a pair of pants and you have the hyperbolic geodesics, you can draw perpendicular geodesics between them and kind of normalize that way. That doesn't seem to be, I'm not sure if that works, but that doesn't seem to be very nice for us, at least. At least there's not a kind of a native notion of perpendicularity, even with kind of the, yeah, so so we had to kind of find some way of doing this. I mean, it uses some kind of choices that I think are due to Banahan and Dreyer. And, but yeah, so because everything is moving, we have to kind of make sure that these things are all well defined. Okay, so I guess I'll say, are there any questions about this stuff so far? So I'll say kind of just a little bit about, I mean, nothing too technical, but a little bit about kind of the ideas of the proof. So we're going to consider kind of this so there is going to be a natural map from this space, and I'll call this thing just V, so I don't have to write it again. And so V depends on C and all this other data. So we have this natural map. Then kind of the idea is to focus on the holonomy. So this is going to be, say, the gamma I as much as possible. Okay? And so what I mean by that is that so remember kind of gamma is from pi 1 of some Sj into PGL3R. Okay. And so what we're kind of motivated by is kind of in the compact case is that I think Dick mentioned this, is that the limit set of this holonomy action gamma, so I guess given omega mod gamma, this is a convex RP2 structure on S, then the limit set of gamma is exactly the boundary of omega, right? And so then if you can control gamma, then you control the boundary, and then that makes things easier, right? So in particular, so if we know, for example, that gamma I goes to some gamma infinity, then that will imply that omega I goes to omega infinity in the case of no singularities. Okay. All right. Okay. So this breaks down in the case that we have to do. And so in particular, maybe I shouldn't have erased that. Maybe I'll keep these up here for a little bit. This is going to be omega. And so in particular, what happens is that we find that there are, in each of these cases, the non-parabolic cases, we get these line segments on the boundary. So here, here, I mean, we just have a kind of a part of a triangle on the boundary here. And so it turns out that these line segments are never going to be in the limit set. And so we need to kind of characterize, so part of what we do is we characterize the limit set in terms of various fixed points, and then we show that any gaps that there may be have to be filled in by these possibilities. Okay? So the idea. Okay, so all right. And I guess in order to get to, so to get from Goldman's coordinates, let's say, to the gamma I, so in order to kind of recreate the full holonomy from these Finchel-Nielsen coordinates, then we kind of, what we do is we essentially use Goldman's machinery of combining convex RP2 structures and their representations, especially across principal geodesics. So back in 1990, I mean, Goldman has kind of a lot of machinery for this, and kind of given especially kind of these modifications that we have with our coordinates, we just follow Goldman's machinery and show that kind of if you have convergent families here, then the whole holonomy converges, not just kind of these unbased holonomies around these, the loops and the Pants decomposition. Yeah? Okay. So that's kind of the idea of what happens without singularities. With the singularities, we have, okay. Let me see what I want to do. So we have kind of the following proposition is that, so if we have omega and gamma, such that omega mod gamma, this is a convex RP2 structure on S, so I'll call it a regular one, in that kind of all the ends look like one of these, or half of one of these pictures, at least. And so S is oriented with negative Euler characteristic, then the limit set of gamma is the closure of all the set of, and I'm going to write this in quotes, kind of attracting and repelling fixed points of non-trivial elements. And the boundary of omega is equal to the limit set union kind of a pi1 equivariant collection of line segments. And the line segments are exactly what you get in cases 2, 3, and 4 here. So we can classify everything here. And what I mean by attracting and repelling is that, well, I'm going to consider this to be attracting, even though it's not quite down here. Because that's, really, you can think about this as at least from the point of view of omega, this acts as a attracting fixed point, and I'm going to consider this fixed point to be attracting or repelling. I'm going to throw those in as well. Okay. All right. Let's see. Okay. And so basically what we can do is, and there's kind of a, I guess I only have a few minutes. Another lemma is that, so, and I guess Dick kind of mentioned this very well, is that in a lot of this theory, it's useful to kind of consider flags corresponding to a given holonomy. So what I'm going to do in kind of this convex case is I'm going to look at the negative fixed point. So this is going to be in the hyperbolic case. I'll call this C1, this point. And then the rest of this flag is going to be given by the tangent line here. So that, that corresponds to, say, this picture here in terms of the hyperbolic holonomy. Well, it turns out that there are naturally flags in these other cases as well. So in the parabolic case, this is C1, and this is C2. And in this quasi-hyperbolic case, I want the repelling fixed point. So this could be C1, and so this line has to be C2. Okay? And then the other quasi-hyperbolic case, we get a slightly different picture if the signs, if the signs are different. But the flags do converge, and this is kind of a fact about linear algebra. But you need the fact that, so I won't kind of go over the details, it's not difficult, but you need the fact that the holonomy that appears have these full Jordan blocks, right? Because if you have kind of two eigenvalues coming together, and you still want to be able to kind of show that the eigenspaces converge, and if this part were diagonal here, then you'd have like a one-dimensional space wanting to converge to, say, a two-dimensional space, and you wouldn't know what the limit would be. Whereas here, there's a perfectly good eigenspace, and you can do that for the rest of the flags as well. Okay? So one would suspect, say, that for Hitchin representations, you want this sort of kind of the Jordan blocks to be as full as possible in these sorts of limits, because you want the flags to persist. What do you think? Okay, so all right. Yeah, so I think that's main. Let me just mention a little bit about this. Is so once we have kind of our machinery about the holonomy, we still apply this to kind of the non-compact case. I mean, corresponding to each of these connected components of S minus C. And once we have this, so the holonomy will get us this far, up to the limit set. And in terms of kind of, we still need to have kind of the omega i's converging with respect to the Hausdorff distance. And this classification result shows this. Well, all we need to do is we need to make sure, well, the quasi-hyperbolic case, just by convexity and simple dynamics, you cannot kind of go, this is going to be in the boundary no matter what. So we don't have to worry so much about this. But what we do need to worry about is that the bulge will actually converge to bulge plus infinity and minus infinity in the correct way. And so we need to kind of have these, kind of write things down very carefully and have a few estimates to show that. But that's most of the proof. Anyway, my time is up. Thank you.